Just to remind you, test number 3. No, test number 2. I get all my numbers all fixed. Test number 2 is next Wednesday on November 3rd. And it would be live. And I have asked the department to remind the TAs, the proctors, who happen to be TAs, for GH section and for GH3 section, that they have to be there to check you in. In other words, they'll have the list of the students, and as you come in, they will have to check you in so that they will be able to tell me who was at MR3 for next Wednesday. And I will make the blackboard not pop up at 5 because it may be a little bit. I will be online just to kind of hear or observe what is happening. But there will be some time because it takes a while for people to check in and to be seated, whatever, so many space, physical distance apart. And then the test, I will then make the test available, and you will have an hour and 15 minutes. All right? That's for test number 2. Even if some people, I don't know, what is it now? So I will control the time it pops up. I'm beginning to be more, let's say, proficient with controlling Blackboard. So I will, when the time comes and is appropriate, I will then click on the right time and then make sure that it is 75 minutes so that you will have. All right. And so the exam will end, let's say we start within 10 minutes, so it's 5:10, and it will end at 6:25. Okay? That's next Wednesday, and you have to be live. You cannot say, well, I fly by, and can I then take the test just flying by? No such thing. That's the college policy, so yeah, it would still be open book in the sense that you have your laptop and you have all of whatever your computer stuff, right? So it's November 3rd. And it will be the same kind of Blackboard fussiness, but now that I know it does not know how to do the scientific notation for small numbers like 10 to the minus 12, I will make sure that it is, in the scientific notation, and whatever number they show you will be the significant number figures for that. Like it is 3.45 times 10 to the minus 12. What it will show you is 3.45, and then I'll add to it times 10 to the minus 12 or 10 to the minus 11. All right, I learned from my lesson from test 1. And it will be again in random blocks. And within each block, it would be, I don't know, multiple answers. And it's room MR3, Mirage 3, same room. If for some reason the administration says not available, they will have to tell me, and I will send you an announcement before Wednesday. But by Monday, it's already, as far as I'm told by our department secretary, it is MR3. Okay. It will again be 15 questions, but they will be in random blocks. So it's 15 questions, but random blocks. And it will cover, let me just get the chapters right for you. It will cover 21, 22, 24, 25. All right. 21, 22, 24, 25. And it will be random block, and within each one it may be multiple answer and calculate a formula in whatever random order. But within each random block, it is on the same, I guess, concept or same situation. Maybe it's best to say same situation, that you then have to say, well, I know the answer. When I'm pushing this rod through a magnetic field, I know what is the whatever you're asking, and you know it, so you can figure out the multiple answer and the calculated formula in sort of the same notation. Okay? Any questions? And no backtracking. We do the same one that we did with test one. No backtracking, but you get 2 attempts. And my advice to one and all, is don't plunge in. You are given basically 5 minutes on average for each question. And what you do is you read carefully the units that are mentioned, because sometimes it may be so many feet per second, sometimes it's so many meters and centimeters. So just be careful of the units. And then since you have all of your notes available, you would then be able to say, oh yes, I should use this formula. All right, then you use this formula, but make sure that you have the conversion factors all straight. And then I'm pretty good at confusing you with the conversion factors in the wrong place. All right, that is for test number 2. Short answer, well, maybe, I don't know. I think short answer is too simple. Yes or no, it's too simple. But anyway, I am working more on things that involve you're having to think, know what concept is involved, and then it may be not exactly what was in the homework. I now ask it from this side instead of this side. It's the same situation, but I'm asking slightly different angle. Okay, so that's why I say you better be good with the concept so that you know, oh yes, this is now such and such. Okay, and the other announcement is the final is on December 15th, Wednesday, and it starts at 6 p.m. and doesn't end till 8:15 p.m. and it is again live. All right, so you better put it on your calendar, because that comes to the near the end of the semester and everybody wants to be going off to the holidays. December 15th, yes, it's a Wednesday. I think it would be MR3, but again, the actual room assignment is up to some guy in the registrar's office who does his own whatever little magic wand and say, okay, you get this room. I don't like you, you get that room. Whatever, I don't know. They will decide, and our department secretary will find out. And it will be announced by then, okay? Any other questions? All right. So now, today we will be on chapter 26. It will be on the next test. This chapter 26 will be on the next test, test number 3, which is, I forgot now, on a Monday, because that's the week of the Thanksgiving. If we have it on Wednesday of the week of Thanksgiving, it's a little bit tough for many people. So I am going to put it on a Monday of that Thanksgiving week. Yeah, is that 20? Yeah, thank you. That's 22nd. All right. November 22nd is test number 3. Okay. Now let us get on with this. Actually, is more interesting aspect of optics. And now we need to, for this part of it, we begin to now have a concept, new concept, which is what is called index of refraction. Because light does get refracted We already learned in chapter 25 that light is reflected, but light can be refracted when it enters through a medium like water, when light goes through glass, or when light goes through a diamond. I mean, if you can afford a diamond. Well, anyway, light, when it enters a denser medium, it gets bent. That's what you call refraction. I don't know the word origin of why it's called refraction. Certainly, I don't know why it's called reflection, but anyway, that's the thing that we now want to have a certain concept, is this index of refraction, because light, when it goes through vacuum, it goes at 3 times 10 to the 8 meters per second, right? It was so fast. And we are not, you are not at this level sophisticated enough to follow Sir James Clerk Maxwell when he put in together Faraday's law, Ampere's law, and Gauss' law, and all together. And then he discovered, whoa, electric and magnetic fields are actually waves. And when there's a wave velocity. And he figured out that C is 3 times 10 to the 8, just from the permittivity of space, empty space, and permeability, epsilon 0 and mu 0. But anyway, that was in chapter 25. But now, when it's going through a material like water, then the speed of light becomes slower. We can sort of intuitively understand that. Then when there's nothing around, zoom, I fly. But when there is now, a lot of stuff, which means a lot of molecules, then I get banged on my head even as I go right through. So I slow down. I slow down not because I want to slow down. I slow down because of those molecules that are banging me. So the light will now travel through that with a less speed. So then we say that the velocity of light in the medium now is less. And how much less is this index of refraction? Index of refraction, the velocity of light in the material, I can re-express this. Velocity of light in the material is C over N. The velocity of light in the material is C over N, or the way they write it is index of refraction is the speed of light over the speed of light in the material. And so you can see that the index of refraction is always greater than 1. You see it? Because the speed of light will get slower. In some material, in some medium, it may be less, like light going through air. Oh, it's pretty close to the original speed. So the index of refraction is 1.003 something or other. I mean, the engineers, the experts have measured the index of refraction of light in atmosphere. And they have also measured the index of refraction of light in water and in glass. So this is then the table that you notice that for water that we need to know, because after all, you swim, you have your ship, we are dealing with a lot of situations where light comes through water. Then the index of refraction of water is 1.33. As far as glass is concerned, after all, I have to wear glasses. I don't know about you. And we then also need to know the index of refraction of glass, which is 1.523, right? The index of refraction is bigger, which means that the speed of light going through glass is slower than in water. But meanwhile, you see in air, oh, it is 1.0000029. So it is very close to 1. Okay? And now for the index of refraction, there is one law that governs the angle in which the light will go into the water. So if I have incident light on, let's say, water, just to take a simple example, I shine light on the water. If I shine light and if the water is still, namely the surface is very calm, then there is some reflection. And remember in the previous chapter, I said in the old days, the people didn't have glass mirrors. Well, they relied on a shiny metal and armor, and then you can see your own face on it. Or they go to a big basin, and then the water is still, then you can look and see your own face on it. So this is then this angle of incidence equal to the angle of reflection. However, the light can also enter into the water. Then this becomes the refracted ray. All right, this becomes the refracted ray, and now the angle of incidence, they now call it theta 1, and over here they call it theta 2, and now Snell, I should have checked who is Snell. But anyway. Well, there is this Snell's law, which actually came very, very early. It was not like in the 16th century, 17th century. I'm sure Mr. Snell was doing this way before. I don't know in which 10th century, 11th century or whatever. And this law says when the light enters into a denser medium, the angle is determined by this law. It is N1, whatever this index of refraction of the first medium, times sine theta 1 equal to N2 times sine theta 2. All right, that is Snell's law. And this Snell's law is very important later when we discover the prism, when we discover the rainbow. Well, we need to know this Snell's law. So actually Snell is around the time of Newton, because Newton was good with prism, and he was the one who sort of first analyzed this, but he did not propose this Snell's law. So I guess Snell is around the age of Newton. Okay? Now, the important way to remember Snell's law is this way. It is whatever is the index of refraction of that first medium times sine of the angle of that first medium equal to the index of refraction of the second medium sine theta 2. Some people will write it as sine theta 1 over sine theta 2 is equal to sine theta 1 over sine is n2 over n1. If you remember it that way, you can easily get confused. But if you remember it this way, it's not so easy to be confused. All right, it is whatever is the index of refraction for the first medium times the angle of incidence in that first medium equal to the index of refraction of the second medium sine of the angle in that second medium. But they are always with respect to the normal. And clearly, if this is dense, it would be bent towards the normal. If this is less dense, it will be bent away from the normal. Okay, so that's the good intuitive way to figure out what would happen to this refracted ray. Is it bent closer to the normal, or is it going to be pushed away from the normal? It all depends on what is your index of refraction in your original medium and into the medium that you're entering. So for example, if you were to shine a light, your torch, your flashlight is in the water itself. If your torch, your flashlight is in the water itself, you will then say, this is now my N1. And the book does give you, right? This is now my N1, and my N1 is 1.33 because this is water. And now the light that comes from this flashlight, some of it would be reflected. Some of it would be reflected, right? But some of it can get through. But when it gets through, because this medium is less dense, it will be bent away from the normal more than theta 1. So theta 2 now would be come out at a bigger angle than theta 1. Again, you use this Snell's law. Are you comfortable with this now? Mm-hmm. Yeah, I mean, it's very easy, right? But the main thing that you need to grasp, and let's say be strong in your concept, grasp of the concept, main thing is this and what it means. The index of refraction of your original medium, like in here, the original medium is water, and this is the angle coming in towards the normal from inside the water, and then this is the outside, where it now goes out, the index of refraction and the angle in that outside. Okay, so now, how to determine? Well, this is just working it out. A light ray strikes an air-water surface, there's air, there's water surface, at an angle of 46 degrees with respect to the normal. Find the angle of refraction when the direction of the ray is from air to water and from water to air. Basically what we already showed, but now just to put in the numbers, right? So to put in the numbers, that's easy. You just say, I now take the first case where it is from air to water, and I know from that formula, n1 sine theta 1 equal to n2 sine theta 2, and you asked me to figure out theta 2, so now I use algebra and I say it is n1 sine theta 1 over n2, but n1 is basically 1.00. It was 1.00003 or something like that, right? So it's basically 1.00. Sine of the angle, you told me it was 46 degrees. And then I already remembered that the index of refraction of water is 1.33. Voila, you do this and you get your calculator, sine of 46 degrees is 0.54. Therefore, the angle of the refraction is 33. It was 46 degrees coming to the water, but in here now, this angle is only 33. That's easy. Well, now you do the second case. Your flashlight is under the water, and you now want to know what is the angle coming out. Sine theta 2, well, that is n1 sine theta 1 over n2, but now n1 is 1.33 because this is where I am. So n1 now is 1.33, and then they say it's incident at the angle of 46 degrees, but n2, which is outside, is 1. It's air. Therefore, now I figure this out, and this says it's sine theta 2. How did I get, where's that, 33? 1.33 is the index of refraction of water. 1.3, oh, how did I get this? That one you now have to use a sine. Since you have already figured out that sine theta 2 is 0.54, a sine of 0.54, inverse sine of 0.54 is 33 degrees. By the way, when you take the test, test 3 and so on, when you do a sine, you better be sure that what comes out from your calculator, is it in degrees or is it in radians? Because scientific calculators, they've been told everything must be in radians. But then you forgot that the calculator only gives you the answer in radians, but Blackboard will only take it in degrees because Blackboard has been told by me to accept, anything in degrees. So just be careful. All right. So a sine of 0.54 is 33 degrees. And likewise here, a sine of 0.96 is 74 degrees. So you can see that it was incident here at 46 degrees, but man, when it comes out, it actually goes off at an angle of 74 degrees. All right. So Snell's law is very immediately applicable to our real life situation. We intuitively already know that, but Snell's law makes it very precise. Okay. Feel free to ask questions because that's how you catch. How did you get 33? How did you get 74? Okay. Now this thing about Snell's law helps you also to deal with something which is again in our daily life we are aware of it, but we may not try to figure it out, but we are aware of it. Have you been to a swimming pool? Have you been to a swimming pool? Yeah, of course. Well, now, have you ever noticed that when you're in a swimming pool and you're, sort of stand on the shallow end? Because if you try to stand on the deep end, you would be drowning. But let's say on the shallow end, you stand in the shallow end, right? Do you notice that you appear to be shorter when you're standing inside the pool? Yes? Must have seen it, right? I mean, every child already says, "Woo, mama, you look shorter now." Yeah. So we all have that. But now we can actually sort of, with the Snell's law, actually figure it out. So this is what you call apparent depth. The searchlight on a yacht is being used to illuminate a sunken chest. At what angle of incidence should the light be aimed? It's related to this issue of apparent depth. Because what happens is you shine light trying to locate this chest. If you shine light trying to locate this chest, if the chest is 2 meters away, what angle should you aim it at so that the light will in fact reach the chest? If you have it over here, then the angle is too big, then you will miss the chest. If it is over here, you will of course miss the chest, because if you shine the light straight down, oh, you say, I don't see the chest. I don't see my treasure chest. So the question is, if in the end you located it, then from the angle, you can then tell the diver, oh, the chest is 2 meters away. Are you following now the direction of this exercise example? If I am, trying to locate the treasure, and if I just shine light straight down, I say, gee, I don't see anything. It's just simply the ocean floor, right? So then I shine it a little further away, and I still see nothing. But at some angle, then I say, I see the chest, the treasure chest. And then someone will say, oh, yes, I'm a good engineer. I will say, oh, it was at this angle. Because the engineer will figure out that when you shine this light, this part of the sea is now lighted, because the light did shine on this. So the engineer will say, oh, this distance now is blah, blah, blah. And you know the height above the water. Therefore, the angle is such and such, theta 1. And since this is the angle theta 1 that in fact shines on the treasure chest, I can therefore figure out by Snell's law that this is 2 meters away. But here, the problem or this example is to, given that it is 2 meters away, what is the angle? Practically, what the engineers need to do is to now search. When you're searching, they will now know the angle by the spot of light on the water, because that's where the light is shining on the water. And then they know from this distance and from the height of this above, they know this angle. And then they say, because I know this angle, I know this angle, and therefore I know it, and I know the depth of this water, the ocean at this point, therefore I know it is 2 meters. Okay, so now you can now work it out. You say, all right, if this is 2 meters away and this is the depth of the ocean here, or of the lake here, is 3.3 meters, then this angle theta 2 is, what is it? A10, right? This is arctan. A10 of 2 over 3.3, which is 31 degrees. And therefore, you can now figure out what angle, because sine theta 1 is n2 sine theta 2 over n1, and n2 is bigger because it's the water, you are outside the water. So n2 is 1.33, and the angle theta 2, you just figured out that it is 31 degrees. So therefore, it's 1.33 sine 31 degrees divided by 1, because after all, this is the air here. And therefore, you now say, oh, I have figured out sine of this angle of incidence, which reached the treasure chest, is 0.69. Therefore, the angle is 44 degrees. And since this is 44 degrees, I know the height above the water. I can also figure out what is this distance. Do you see trigonometry being used here? You better be good with trigonometry. All right. Any questions here? You see, even as I am explaining, I am introducing different angles. I mean, the different aspects. The book example just simply says, I know this one is 3.3 meters deep, and I know that it was 2 meters. What is that angle? Whereas the way I ask is, I would like to know, how far is this treasure chest? By knowing how far this, what do you call it, this distance is, because I shine light, and at that distance, if I know this distance and I know my own height of this searchlight above the water, I can therefore figure out theta 1. And because I have figured out theta 1 and I know the depth of the lake, I can then tell the diver to say, you swim out there, which is 2 meters away from under my boat, and then you will find it. All right, so there are always different aspects of the same situation, but different aspects. Okay, any questions? I'm not going too fast, right? Okay, so now let's go on. And now the question is, remember I said, well, everybody, even a child, would say that, you seem to be shorter when you're inside the water, when you're standing inside the shallow end of the water. And so we would now like to know, what is the apparent depth? Well, the book has this as an example of apparent depth. What do you mean? Because you see, we already said that you have to shine light at a certain angle. What was it? I forgot. 60 something degrees, right? Then you locate the chest, which then you say the diver, it is 2 meters away. But now, as far as the engineer or the one who is searching, it looks like when the light came from the chest, it got bent bigger, right? Because when the light came from the chest, this is the n2, and this becomes n1 sine theta 1 is n2 sine theta 2 because it's coming from there, and now it's bent away. So now it will now seem to come from here. Are you following this diagram? You know, light that comes from a dense medium, when it comes out, will be bent away from the normal. It is coming from the dense medium. After all, water is denser than air. The light from this treasure chest now gets bent away from the normal, and therefore, as far as this engineer, the guy who is searching, he will say, oh, the light seems to come out in this direction, so it seems to come from here. Therefore, the apparent depth is less than the actual depth, just like the little child already figured out. The little child already figured out because the little child knows how tall the mother is. And now the mother looks like, the bottom part of the mother is now shorter, right? So apparent depth, you would like to now know it in terms of the index of refraction. And they now show what the light ray from the treasure chest, when you are above it, what is the apparent depth? Well, light ray that comes this way gets bent away. Light ray that comes this way gets bent away. So it seems to come from a shorter depth, right? Because if you go backwards, it is at a shorter depth. That's the apparent depth. And if you work with the equations for angles that are small, I mean, this is now technical. I don't know whether you learn it in your high school trigonometry. Sine theta 1 for small angle is the same as theta 1. Well, maybe I shouldn't talk about such. Just if you are not good with that aspect of trigonometry, just simply say, yeah, okay, I got it. So you say, leave it to the engineer. But what I will get from the engineer is that the magnification, or how much it is less or how much is more, is simply a ratio n2 over n1. So d prime is the distance. Where is the apparent depth? D prime is n2 over n1, but in this case, n1 is bigger than n2, so the actual depth is less. The apparent depth is less than the actual depth. If you are good with the sine theta for small theta and so on, you can actually work it out from this diagram. But anyway, let's not get into it. Let's just take the engineers who says that, oh, we have actually helped you with the trigonometry here, but now we are talking about this apparent depth, and you either work over here or you work with this, but the result that comes from either working with this diagram or with this diagram is that the apparent depth is less than the true depth by this ratio of n1, n2. I mean, you already see visually this, and then you just have to work out the trigonometry. This one is where the angles are not that small, but nonetheless, trigonometry works, whether the angle is small or big. But over here, the angle is much smaller, close to, because you're above the treasure chest. And then you can work with the approximation. Sine theta 1 is theta 1, sine theta 2 is theta 2, provided theta 1 is radians and theta 2 is radians, and they are the same unit. And then you can figure it out here. All right, I think let's not get too involved with the engineering aspect. And now, there is a very interesting, again, progression of concept. On the inside, looking out. namely you are the diver. All right. A swimmer is underwater and looking up. If now you are the diver looking up at the surface, someone holds a coin in the air directly above. Again, this is apparent height now, not apparent depth, but apparent height. To the swimmer, the coin appears to be at a certain height. The question is the apparent height of the coin greater, less than, or the same as the actual height? In other words, now we're not looking at the treasure chest and find that its apparent depth is less. We are now under the water, and then we're looking at this, not treasure chest, but just a coin. Now, maybe this is a expensive coin, right? So you're looking at this coin, and someone holds this coin, and this coin is only at a certain height of, maybe 3 feet, 1 meter, or less than 1 meter. And the question is, for you, when you are under the water and you are looking at this coin, does the coin appear to be higher or lower than this actual height? Now, you haven't yet sort of become a good, engineering aspect. So let us now let the book show us. And the book says, if you have a coin and it actually is coin above you, and this coin sends light rays, well, because this is less dense medium and going into a dense medium, the light, when it comes to this water, it enters the water, it will be bent towards. It will be bent towards. All right. So if it's bent towards, it will now come down here. It will not go in its original straight path, which would have been this way. I'm not having it well. Yeah. It would, if there were no bending, it would have gone straight on. But it got bent towards the normal, so therefore it comes closer. But now if it comes closer, you are down here. You will say it seems to come from here. I guess this picture is not that. Are you are you able to see it? Yeah. I mean, you need to, yeah. You see, the light from this coin, let's say the coin is at an actual height, which is D. You now say the light ray from this coin came to this surface of the water, and then instead of continuing on, which means that it would have gone straight this way, now is bent closer to the normal. Because it get closer to the normal, it therefore seems to have come from a higher place. Do you follow? It got bent closer to the normal. I guess they should have drawn a diagram that magnifies it even more, but they didn't. I'm just reproducing the picture here. I should have looked in the internet for a better picture of this. I cannot draw a diagram like this with my tools that I have. But anyway, do you see it? This light ray came from the actual coin, was coming this way. But because it came into the water is denser, it is bent towards. Since it is bent towards, it now will be this way instead of the original path. The original path would have been like this. So it is now bent closer towards you, but you will now say, well, it seems to have come from a higher place. Because as far as you're concerned, it came to me at this angle, so it would seem to come from a higher place. Therefore, the apparent depth from me who is inside would look to be larger. The apparent depth, d prime, is, I put down here, n water over n air. I don't use n1, n2 because it didn't say n1, n2 here, so I put it as n water and n air, right? So d prime is now higher because the density of water is higher than the density of air. Now we will come to a trick question. But anyway, this is just to prepare you that when you're looking at someone in the pool, you're outside, you say, hey, you become shorter. But if you were under the water and you're trying to look at the, I guess, whatever coin or a tower or something, and you will say, ooh, it looks like it is much higher. Oh, I thought I had one trick question, but I guess the trick question comes later. The way Wiley Plus does it, sometimes the order. Oh, you're saying, how do we know this? Well, that's where you have used the trigonometry to figure it out. We are interested in what is this apparent height. And since you already know this angle, their relationship by Snell's law, you know this. Because if you know the Snell's law, you know this angle relative to this angle. And now, because you now know that this came all the way from here at whatever was this smaller angle, then it is at a higher height. Why? Because the base is the same. Are you seeing the trigonometry here? The base here is the same, and this height depends on the angle of incidence. But now, because of Snell's law, because this light ray had to be bent closer to the normal, this angle is smaller, but this is still the same. Therefore, the height, the tangent now is higher. Incidentally, sine theta becomes the same as tangent theta when theta is small. What was the question? I didn't catch that. What was the question?
How do we know it's n water over n air, like, and not the other way around?
Yeah, no, that's where you have to write out the Snell's law and then make use of the fact that the place where this thing lands on the water is the same whether you are from this side or from this side. And then as far as the angle is concerned, theta 1 is this theta 1. It's the angle with which it hits. But now n1 sine theta 1 is equal to n2 sine theta 2. But for small angles, theta 1 sine theta is the same as tangent theta. I guess that's the better way to remember it. For small angles, sine theta is the same as tangent theta. Therefore, Snell's law now becomes like n1 tangent theta 1 equal to n2 tangent theta 2. And then trigonometry takes over and says, well, but I know this side is, let's say, whatever, half a meter. And therefore, I know the height. Because the height, this over this, tangent of the angle, is this over this. But now, tangent of the other guy, theta 2, is this over that now. And then you work it out. That's indeed n1, n2 is n water, n air. You have to work out the intermediate step. I didn't work it out. I didn't show you the steps yet. But the main trick, two things you need is sine theta becomes tangent theta for small angles, and then you modify n1 sine theta 1 equal to n2 sine theta 2 as n1 tangent theta 1 equal to n2 tangent theta 2. And then the situation is that tangent is this half width divided by the height. And tangent of theta 2, I mean of the water, inside the water, it is the same thing over d prime. And that's how you get this. I cannot use my stylus to write it because ever since there was an update in the version, I have lost my ability. But let's go on. Is that okay to go on? If there's no objection, let's go on. Well, now this is another aspect of this Snell's law, is the apparent displacement by a slab of material. Again, you may not realize this, but let us say that you are near Empire State, and you're in an office building that has a glass wall. As you walk past the glass wall, right? Because there are some of these office buildings, they are very fancy. They have the glass ceiling, wall. They can pay for it. They don't mind it. So they have this glass wall. And as you're walking, you will notice that the architects, they want to relieve your stress of workplace. So what they do is there is one pane of glass here that is slightly thicker than the next pane of glass, and it comes back to the same pane of glass thickness. You don't realize it, but you're walking, and then what you see is that the Empire State seems to be over here, then shifts over there, then shifts back over here, then shifts back over there. And it all has to do with this effect. And now let us see, how does this effect come about? It is nothing more than Snell's law again. I have a light, and let's say that came from the Empire State Building. So it now is incident on my slab of glass here. Let's say it's glass. So now it will now be, because glass is denser than air, it will now be bent towards the normal. So you have now theta 2. So now the light that comes from Empire State outside comes in, gets bent over here. And then when it comes to this side of it, it is now coming out of. It's going to come out of this dense medium into a less dense medium. Therefore, now it will be bent away from, right? So it will now be bent away. But now you say, I know it's the same N1 and N2, the same material, but now it is opposite. It is now bent away. So as far as this is concerned, the Snell's law here, which is sine theta, N3 sine theta 3 equal to N2 sine theta 2, but N3 is the same as N1. Therefore, theta 3 is the same as theta 1. You got it? And what does that mean? That means that this light ray will now come out, and it will be in the same direction as the incident ray, but just shifted. How much is it shifted? Oh, Snell's law will tell you. Trigonometry with Snell's law will tell you. Are you following the general drift? Right? The actual amount, then we have to, of course, be a little bit more precise and use trigonometry. And then you have to tell me what is the thickness of your thing, because trigonometry comes in here. But until then, what Snell's law tells us is this angle is the same as this angle. Therefore, it's displaced. Oh, okay. And now the book says, we can actually have a derivation. Now, we don't have to go through the actual derivation, But I want to now, let's say, remind you, have you ever seen a marching band in the field or with a football field? Do you ever, when you're high school, did your high school have a football game with a marching band? You must have, right? Yeah. I mean, we all enjoy it. Now, a wave front, because you remember a light wave is sort of like a wave front. A wave front is like a marching band. The wave, they are all marching, 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 marching with a certain velocity. Of course, in the football field, the marching band only goes at, I don't know, 1.5 miles per hour. They are not going to go at 3 miles per hour, or maybe they are going at 2 miles per hour, but anyway, very slow. Of course, these guys, these light, oh, they are very fast, but for the moment, we are not interested in, how fast. All we say is, it is a marching band, right? It is a marching band that is coming at a certain velocity, which in this case is 3 times 10 to the 8 meters per second. However, the same marching band now has to go at a slower speed, right? Why? Because I don't know if it's Professor Snell or Professor somebody, or maybe it's Professor somebody. Somebody discovered that indeed inside this material, the speed of light is less. So you are the marching band. You are now coming. But now when you're coming, the guys over here on the right end of this marching band, they will hit this medium, and then the medium says, go slow, go slow, go slow. Right? You got the idea? Because once they enter into this medium, the medium is saying, hey, like there's a police, there's a whatever guard that says, you must now go slow. You cannot go fast. But these guys, do they know that you are going slow? No. They just say, yoo-hoo, ha-ha, yoo-hoo. I'm still going at the 3 times 10 to the 8. Meanwhile, these guys now have to go slow. So then what happens to the marching band? It looks like it is turning. You see it? It is now turning so that in the end, even when these guys down here come in, now you again are in unison and everybody is going at a slower speed. But that already now means that the angle is now smaller. Original angle is theta 1. This new angle is theta 2. And now let the engineers now figure out the Snell's law from this. Nothing more than this fact that your wave that was originally at this certain speed, therefore has a certain wavelength, lambda, and now it will now come to with a different wavelength, because you remember the velocity c is lambda times f, and the frequency is the same because they are going at they have a certain frequency. That frequency remains the same, but your velocity has changed, therefore your wavelength has changed, and now it will have come over here with a shorter wavelength. And again, trigonometry helps you to figure out Snell's law. We don't have to work it out. Let the engineers tell us, yes, Professor Snell has already figured it out. All right. So now let us proceed or progress in our grasp of this index of refraction, this Snell's law, and come to a very important application, something called total internal reflection. You remember when actually we go back to that picture, light gets reflected, but light also gets refracted. And now what we want to now know is, if we were in the medium that has a larger refractive index into a smaller refractive index, what can happen? Well, we already know that when you have light that passes from the water into the air, the light ray that comes out from the water will be bent away from the normal. All right. And so we say, yeah, I already know this. If I have light that was from this flashlight over here, if I have a flashlight over here and I'm trying to shine the light out, well, there will be some reflected ray, because after all, this surface is like a mirror. There will be some reflected ray, but there will also be some refracted ray, and the refracted ray will be at a bigger angle because this one is a less dense medium. All right, we already learned this from Snell's law. But now the interesting question comes up. The interesting question is, what happens if I now shine the light further away from me? You know, at first I was trying to look up, so I shine the light up. But now I am interested, like even as a child, but for a diver, you're more than a child. You are now shining the light further away from you. Well, if you shine the light further away from you, the refracted ray will have a bigger angle, right? Because if at first it was only 10 degrees, maybe this is now, like maybe 20 degrees. But now I shine at 20 degrees, it is now maybe 45 degrees. Well, at some angle, the refracted ray will be at 90 degrees. You follow this? And that will be the critical angle. All right, I just want to build up this concept. It's a progressive building up. First, I shine the light more or less at the ceiling close to me. Well, that angle is, I don't know, maybe 10 degrees or 15 degrees. It will then emerge into the air outside because we are under the water, and it will be at, I don't know, let's say 30 degrees. But now I shine further away from me. Therefore, the angle of incidence is now bigger, but n1 sine theta 1 equal to n2 sine theta 2. If sine theta 1 is bigger, the rule about trigonometry is sine of an angle 0 is 0, but sine of the angle gets bigger and bigger and becomes 1 when it is 90 degrees. That's trigonometry that you learn from high school. Well, therefore, if I were to now shine the light down here such that by Professor Snell, the angle of refraction would be 90 degrees, I would now call that critical angle for a good reason. I will call that critical angle because that's the angle where the refracted angle, the refracted ray, is at 90 degrees. And that is n1 sine theta 1 equal to n2 sine theta 2. But sine theta 2 now is 1 because it's sine of 90 degrees. And therefore, this critical angle is n1, which is my water. The air is n2, and n1 is greater than n2. And now, if I now shine light further away, I didn't shine at this spot, I shine over there. If I shine the light over there, my angle of incidence is now bigger than this critical angle. But Snell's law says, sorry, I cannot help you now. Snell's law says that your theta 1 is now bigger than the critical angle. There is no refracted ray. Snell says no refracted ray. because you cannot have another angle that's greater than 90 degrees. So there is no refracted ray, but you still have reflected ray. And so you call that total internal reflection. And this phenomenon is very important for you and for me, both in terms of what you now call fiber optics, both in terms of what is the kind of application. Oh, we will find, I was trying to recall an application, but total internal reflection, we will discover, is important for rainbows. And for many other applications, it is in our daily life. All right. So are you now able to grasp that there can be total internal reflection if you are in a dense medium and what's outside is less dense? And it's important to know what is the angle of critical angle for water. If you know if you know that N1 is 1.33, N2 is 1, can somebody work out a sine of 1 over 1.33 while we're at it? Can somebody do it? You take 1 over 1.33, so that's a point something, point. And then you take a sine of that, and then make sure that it gives you the answer in degrees. What is the how many degrees? 49? Yeah, sure. Huh? I mean, I don't quite remember what it was. I know it's 40 something. You say it's 49? It's 1 over 1.33. Oh, it's 1.333 just to be more accurate. It's 1 over 1.333. And then you say a sine of that, and the angle is what? You said 40 something. Is it 49 or I thought it was 42? 48.8. All right. Okay. So it's 49. We'll. All right. So now that we have sort of begun to grasp that there can be situations where light, in a way, you can say is trapped, right? Because here you can say light is not fully trapped. In fact, there's a part of it that gets free. That's the refracted. And the engineers, when they actually do optics as an engineer, they can actually figure out how much of it is reflected, how much of it is refracted. But those require a lot more understanding of this whole process of light propagation through a medium. But in any case, light can become trapped. Why? Because now there is no more refracted, everything is reflected. So it's like light is trapped. And now there is an aspect of this involving the diamond. Well, okay. Does anybody have a diamond? I don't have a diamond. How much is this diamond? I don't know. Do you have a diamond in your house? I guess maybe your mom has a diamond ring. I don't know. Well, a beam of light is propagating through diamond and strikes the diamond air interface at an angle of 28 degrees. I mean, this is just an example in the book. Will part of the beam enter the air, or will there be total internal reflection? And so here is the situation. I have a beam of light and it is now striking this diamond, and the diamond has this shape here, which they have it over here. So you have the diamond, the light entering the diamond, and you are, I can't read this, the critical angle. Oh, well, the critical angle, because you know this is glass and this is air, the critical angle is small. Maybe this is one that is 42 degrees. Maybe I got it all mixed up. Maybe for water it's 49 degrees, and for glass it is 42 degrees. Anyway, the critical angle is smaller than the previous case for water. And what happens is this light now comes in, and it was incident at 28 degrees. So this is the normal. This is the normal, and it will be bent towards the normal. So it got bent over here. And if this is 20, incident is 28 degrees, this one now would be less than 28 degrees because it's bent towards the normal, and therefore it now will be greater than the critical angle, because the critical angle is 42 and this angle is now can somebody help me with this? Anyway, the book has worked it out inside the, if you look it up. Whoops, I better get the, I mean, just take it as it is, that the angle that now strikes this side, this face, the angle it strikes this face is now greater than the critical angle. Therefore, there is total internal reflection. All right. I mean, you can work out, given that this is 28 degrees, and therefore you know what is this angle because you know Snell's law, and therefore you know this angle, and it turns out to be greater than the critical angle. It will now have total internal reflection. And then when it comes over here, well, first, when it comes over here, this thing will now emerge, because this now will now be within this. It will now have refracted ray and reflected ray. So that's how the diamond has a sparkle. It has these internal reflected that adds to this light. This seems like this is bright and this is not, darker, this is bright, this is darker. So you have a sparkle. And now this is the opposite. If this is surrounded by water, well, then the water, between water and glass, oh, the critical angle is bigger. So therefore, when it comes in here, there is no total internal reflection. There will be some refracted ray going out. So it has lost its sparkle because some light come out to the other side. Is this at least vaguely okay? Yeah, I mean, the main thing is you let the engineers tell you that the critical angle for glass is such and such. Between glass and air, the critical angle, well, not glass, this is diamond. So you have to look up the critical angle, the index of refraction for diamond. The critical angle for diamond and air, the angle is such and such. And now with 48 degrees or 28 degrees, you can work out what is the angle, and then you'll find that when it comes in through this face, it's bigger than the critical angle for diamond air. And you then have this nice sparkle. But when it is through water, you then have to look up the table that tells you what is the index of refraction of water and the index of refraction of diamond. And then the critical angle is bigger than in this case. And because it is bigger, when you have light that comes in, oh, there can be now, doesn't have to be all totally reflected. There can be refraction. And so there will be some light that go through. So there is less sparkle. All right. So at least get that in your grasp. Oh yeah, this is working it out for you. All right, I forgot that the book actually shows it to you. They have figured out that the critical angle is n2 over n1, and n2 is over here. N2 is air, so that's 1, and over here n1 is 2.42. Therefore, the critical angle is 24 degrees. Whereas for this case here, the critical angle is your n1 is trying to come out. So N1 is glass. No, N1 is the diamond. Yeah, N1 is the diamond, 2.42. And outside is glass, is water, 1.33. And therefore, they find that the critical angle is 33 degrees, bigger than in this case. And so the light that came through the diamond, can be refracted outside. All right, so this is putting the calculation that was missing in the previous slide. Well, this is now asking this brilliance, which we have already done. But now, oh yeah, for glass to air. Did somebody calculate for me it was 49? How come I got from internet 42? Or maybe what you did was for water? You did 49 degrees, was it for water to air? Oh, water to air. This one is glass to air. So all right. So then we are all right. We are both okay. I just downloaded from the internet. The critical angle for glass to air is 42 degrees, and we want to apply it to now a prism. If I have light coming in, let's say on this face of this prism, right? It of course will go straight in because the angle of incidence is 0, and the angle of refraction will be 0, so it will just go straight in. But when it comes on this side, the angle of incidence is 45 degrees. But because it is 45 degrees, it's bigger than the critical angle, right? And if it is bigger than the critical angle, all of it is reflected. Total internal reflection. All of it is reflected. And then when it comes here, all of it goes through because the angle of incidence over here is 0. So it will just go straight through. So this then just says that if I orient my prism in just this way, this is as if it's a mirror. The light, all of it comes in, all of it gets come out. All right, so then you say, ooh, that's nothing more than like a mirror. But if I reorient it opposite way, I have this face now facing the incident light. If I have this face facing the incident light, this incident light comes in here, it will now be hitting this side at 45 degrees, and it will be, of course, totally reflected. But now, when it comes to this side, this one is also 45 degrees. That's trigonometry. If this is 45 degrees, this is also 45 degrees. Therefore, this is also bigger than the critical angle. Therefore, it will again be totally internally reflected. And so, what happens? I change the orientation of the prism. I get all of the light reflected. Reflected straight back. It's like I have a plain mirror and you are shining straight in, it will come straight out. This one is a slanted mirror. What comes in, it goes out 90 degrees. But in this case, it's like a plain mirror that is this way. All right. But now, how do those engineers, optical people, companies make use of this simple effect of total internal reflection? Have you ever seen a binocular? A binocular, you now have the light that comes in, and then it actually arranges it so that it gets totally internally reflected, and you see it through your whatever the binoculars here. So the optics here is really clever use of total internal reflection. Industry by now is so advanced that this is but so simple. I don't think there is I guess if you're a professional, you pay a lot for a good, well-designed, well-built binoculars. But it involves a lot more issues than what we do down here, because there's a question of whether there's any spherical aberration and so on. But they have advanced so much that they are able to handle all of that. This is but the simplest basic principle involved in the making of this binoculars. But now, today, we actually make full use of total internal reflection so that we can even see through a corner. That's what fiber optics is, that you can indeed look around the corner of the corridor by this. And medical people, they actually use this fiber optics to look inside your intestine, because your intestine, of course, is not a straight hallway. It in fact goes around, and what they do is they have this fiber, and for the fiber, the index of refraction is high, and by now the industry know what kind of fiber to use. If you were to ask me, I wouldn't know. Certainly I would not use a glass because that's not flexible, but they know what kind of plastic. And by now they have developed materials that are very good plastics that can bend, and the angle of total internal reflection is such that when you have light that comes in here, it will all be totally reflected internally, and you then have, well, the critical angle is theta c. Well, that's what this example. Later on, I think I have imported a slide that shows the application. Well, this is for engineers. When you have light that comes from the sun, it is not polarized. So it's a mixture of whatever orientation, perpendicular orientations. So it has both orientations. But when now it hits the water, like the ocean, there will be some that are reflected. But when it gets reflected, only the orientation is the electric field can only oscillate along the surface of the water. In other words, there's light that comes from the sun. There's electric field and magnetic field, and they are all orientations. You have electric field this way, you have electric field this way, you have electric field this way. It's all orientation, so it's not polarized. But when it now hits the water, the water, the molecules, those electrons inside the molecules, they only oscillate in the direction of the surface of the water. The electrons are not jumping out of the water. The electrons are not jumping out of the water. So the electrons can only go back and forth along the surface of the water. Therefore, when it's reflected, the electric field that comes from the reflected ray has to be polarized in the direction of the surface of the water. That's what they are trying to show down here. You see, this is the surface of the water. So it is along the direction of the surface of water. So the reflected light from the surface of the water is now polarized, even if your original light was not polarized. All right, can you sort of uh, appreciate that? Because the electrons, the electrons inside the molecules, they can only respond to electric field, and when they do, it is in this direction of the surface, and when they do, they are radiating, they are therefore reflecting the the light, and when they do, the light that is now radiated by these electrons that are vibrating, they will now be all polarized in a plane that is parallel to the surface. And there is, however, a what do you call, refracted ray. But the refracted, or inside, you have electrons and molecules. They can now both vibrate along the direction of the plane of the surface, but also perpendicular, because they are now inside. They can vibrate this way, they can vibrate that way. So you will have partially polarized refracted light. And there is this engineering law called Brewster's law, but we don't have to worry about that. So I put down here for engineers, just to know that there is now the effect of polarization. And for you and me, again, it is a good thing that you use sunglasses when you're on the beach. It's good to have sunglasses because then it cuts down on the glare. And the light that comes from the surface of the water is also polarized, so therefore you reduce the glare, both from whatever is the sunlight itself, but also from the surface of the water, because the surface of the water is also sparkling. Okay, now I want to come to a very interesting, which I downloaded from somewhere else, not from the book. And that is, have you ever seen a Mirage? Maybe I will go to the next one, then you will say, have you ever seen a mirage? Oh, I guess you have not been to a desert. I don't think you want to be in the desert, yes. If you were stranded in the desert, life is not easy, yeah? You'll be hard, right? Because that's why it's the desert. It's not, and if it is hot, do you realize that the air gets heated up, right? You know, right? When you're on the beach, the sand is hot, then the air near the sand is hot. And do you know hot air rises? I guess in 203. Did you do that already? Yeah. So you know that hot air rises. What does that mean? That means that the density of air, of hot air, is it higher than density of cold air? how do you compare? Density of hot air versus density of cold air. Which is higher? Which is more dense? Let's put it this way. Cold air is more dense. All right. So now, knowing this, we now look at this as different layers of air, right? Let's now say we look at it as different layers of air, right? Because this is, after all, a medium. You have the hot air, which we call rarer medium, rare in the sense that it's less dense, and then cooler air above. The air is the hottest, right on where the sand is, but then above it, it is denser. Okay, but now if you have a let's say light that comes, when it comes from the dense medium to the hot medium, what happens? When it comes from the dense medium to the hot medium, what happens? Does the light get then closer to the normal or away from the normal? From the dense to the rare medium, what does the light get? How does it get refracted? How does it get refracted from a dense medium to the less dense medium? How does it get refracted? Does it get bent closer to the normal or away from the normal? You see, this is the normal, right? Does it get closer to the normal or away from the normal? From dense to less dense? I need my unpaid assistants to help me here. Away from the normal, right? So it was coming at this angle, now it get away. But now if it, and it keeps getting further and further away, right? Because this dense, there are quite a few layers of air, you know, right? So as it comes down to near the hot air, this angle of incidence here is now greater than the critical angle. There is now total internal reflection. All right? And therefore, what you see seems to come from here. Do you follow what this picture shows? You have to grasp the concept. Because cooler air is dense, hotter air is less dense, the light from here gets bent away and away and away, so that by the time it comes to the lowest level, it's like in the fiber optics, no? It is now at a big, angle greater than the critical angle. Therefore, there is total internal reflection. Therefore, what you see is like, hey, I see it coming from here. All right? You say, oh, I see this tree down here. But mirage is not a question of a tree. Mirage is more a question of, I am in the desert. I am hot. I need water. Right? Don't you need water when you are, wandering around in the desert? Do you need water? And my camel also says, yeah, I'm hot. I need water. Yeah. And now what you see is, this is not the top of the tree. This is the blue sky. Because after all, there's sunlight. Sunlight from the sky above is blue. In the desert, they don't seem to have a lot of thunder clouds. Right? The sky is blue, so what you see is blue light. But what you now say is, oh, far off in the distance, it looks like there is an oasis. Why? because if there is an oasis, the oasis would be blue, reflect the color of the sky. You follow now this picture? It is blue light from above. It is blue light from above. But now it looks like, oh, I have a blue light down here. Because this part, far off in the distance, I see water. I see oasis. And so I want to now go more, more. Here, camel, now I flog you, go further and further. But because it's a mirage, you go further and further, you say, it's still further away. You go further and further, it's still further away. You see now this thing about the mirage in the desert? You have to be aware that there are mirages, and it is entirely due to this index of refraction, this Snell's law, and this phenomenon called total internal reflection. Are you okay with this thing about the mirage now? Okay. Oh, and then there's this fiber. Yeah, there's this thing that I also downloaded from my other class, where you have the total internal reflection. So we see water even though there isn't any. Yeah, that's right. Because in the distance, it looks like the sand is not blue, right? The desert, the color of the sand is all yellow, it's different shades of yellow. But then somewhere ahead of you, there's a patch of blue among the sand. And of course, you say, therefore, there must be an oasis, right? Oasis. And therefore, you say, I am now coming to an oasis and I can now rest and drink all the water. But unfortunately, you get closer, closer, you still don't see it. Closer, closer, you still don't see it. Closer, closer, it gets further away. And now, do we have time? Yeah. Let me just quickly mention, for the total internal reflection, there's another application, which is that you are underwater and you now want to look at what is around you, and what you can see is you're looking up and there is the person and that's the tree. What you see is within a certain cone, because only within a certain cone, which is 49 degrees, do you see. And anything beyond that, all you see is not the sky. You don't see, you see the slope of the lake. You see, for anything greater than 49 degrees, it really came from this side, which is the shore or the lake, the side of the lake and the side of this lake. So what you see from down as a scuba diver is you see the blue sky above you, and then you see your friend over here and the tree over there. But outside of that, what you see is instead the ocean floor. It's an interesting effect. If you're a scuba diver, you are familiar with it. But if you're not a scuba diver, you say, what happened? All right, it's 6:40. I will stop here. We will resume on Monday, and by then I will have already set up the test, and I can then go over the important aspects of test 2. All right. So meanwhile, what? Somebody had a question? Okay, so stay safe.
Professor,
Yes.
quick question.
Yeah.
This is Oscar. I have a quick question. Following up with recitation, I'm in the room right now, but no one's here. I'm just wondering because internet connectivity issues on campus are a huge issue, and they just have been, I don't know, for me and for a lot of people.
Yeah.
Uh, Okay, so recitation. Currently in the room, no one's here, not even the instructor. I don't know if he sent out an email about recitation being online or not.
I
Um,
don't. I have not. Yeah. Right.
but also for the next exam, I didn't get this because I was having a hard time connecting at the beginning in the first hour. But is there any way for some of us, if we wanted to get like a paper exam instead of doing it on the computer just for the sake of these connectivity issues? Because I went to MR3 and MR4 just to recheck if it was a one-off thing. And every single day that I've had recitation or I've came to campus, I don't get more than 4 megabytes per second for my
Yeah.
connection, for my internet speed. And that's not enough to even stream class, nor is it going to be able to like download JPEGs, especially if everyone's on at the same time. I'm just wondering if I would have to either go through accessibility to get that exam done separately in a separate room or something, or if there's a paper option, just regular paper option.
Yeah. No, that gets more complicated because then someone has to print it out and someone has to collect it and then somebody has to give it to the grader. It gets complicated. I will check with the department as to what the so-called connectivity issue is, and then we'll decide by Monday what to do because it's very complex.
Yeah, Victoria, I did connect to CCNY Wi-Fi. But also, Professor, I'm just in the instance of like computer failure, complete failure. There should be an alternative to students that are having these issues. Uh,
Yeah,
it can't solely depend on a good connection and on a good computer.
yeah,
Even that, the fact that I do have a good computer and I should have a good connection.
right. The other thing is you better make sure that your computer, laptop, and so on is charged fully because if somewhere halfway you say your laptop ran out of battery, I cannot help you, and you have to do it yourself.
Yeah.
What the college has to provide is connectivity, and they already said that they have been working on it, and they have been working on it for the last week or so. Because I sort of remember they say there was some connectivity issue, but since they want it to be live, they have to solve the connectivity issue.
Yeah, I don't know. It's been a consistent problem. I came from IT just now, and they said
Yeah,
that it could just be Apple devices, because they tried it with other Windows computers, and they said that they were having normal connection speeds. But I'm not sure if it's this is just oh I really don't know what it is, but that's why I want to make sure that if in the occurrence of last time, if something
yeah,
happened, there should be an option. On paper, I'm sorry, Professor. I know that like it's an issue, but at the same time, if this was in person, it kind of wouldn't be an issue. This would be the
yeah.
same.
Well,
Or being able to take it in the lab room on these computers would be great in our lab classrooms. How
yeah,
do you
I
even
don't
be
know.
open to that? Because exactly the same time. It's hours. It's a 1 hour difference. If we're taking it on Wednesday, GH3 has lab afterwards. So
Yeah, well, I cannot sort of help you in terms of these technical issues, but not everybody seems to have the same issue, even with the Mac. So it probably you need somebody to help you with your settings because your Mac, with these each update, there are these little settings here and there that make you hard to figure out. But indeed, in the end, you did figure out because you were able to do the exam. So it's not that it is impossible. All
it's
right.
not an impossible. It's just an inherence for. I
Yeah.
mean, I know I went to the IT department and they helped me out, and it wasn't a settings issue. It was just weirdly enough, a couple devices in the IT office were not getting more than 4 megabytes per second. which presents to be a problem, especially if you're trying to attend class before an experiment or recitation, as everybody in
Yeah.
GH3 would probably do, or
Yeah.
for taking an exam where a question is based on 4 different downloaded images.
Yeah.
I mean,
Uh,
we don't have to talk about this right now.
yeah.
Uh,
Yeah.
we can discuss this later, but I just wanted to bring it up, Professor, and I appreciate your time and I appreciate your courtesy.
Okay. Okay. All right. And somebody says you can also borrow a PC from someone. So I don't know. Work it out. Work it out because it's not impossibility. And the other thing is, in life, you will meet with such things and you will need to work out things. So you cannot say, because I cannot do it, therefore the whole world has to change for you, right? So I'm trying to teach you as a life issue, you work with it. And if you have difficulty, you work with other people who can help you and maybe even lend you a PC if you get a friend that has a PC that has no issues, you know. So I'm not trying to say, oh, therefore, no, therefore, yes, therefore this, therefore that, because it gets very complicated. So sorry if I cannot answer every one of your issues. Okay.
Okay, Professor. Thank you. I
Okay.
appreciate that.
Yeah. Okay. Bye. I think we need to stop the recording now.